In the spring of 1942, as the roar of piston engines echoed across airfields from England to the Pacific, a handful of engineers in a hidden hangar near Dayton quietly propped open aircraft canopies and peered at the propellers. They were searching for speed, not just a little more, but a leap. Because in aerial war, every knot mattered, every second in the climb, every meter in the dive. Among them was Frank Caldwell of Hamilton Standard, whose obsessive focus on the blade became the gateway to a new era in airborne warfare. Traditional propellers had reached limits, tip speeds nearing transonic shock, blades churning through dense air, losing efficiency and making the difference between survival and defeat. Caldwell's team asked a radical question. Could the blade be redesigned, not just in shape, but in rhythm, in pitch adaptation, in how it cut the air? The answer would come in the form of a deceptively simple innovation, a constant speed, variable pitch propeller that automatically adjusted its blade angle and engine load, allowing the warplane to pull away from enemy fighters, climb higher, dive faster, and above all, stay one step ahead. When the first F-4U Corsairs and P-47 Thunderbolts rolled from the factory with their new Hamilton Standard units, their adversaries recognized something different in their speed charts. Their rate of climb, their ability to zoom and evade. The secret blade was not just an accessory, it was a revelation embedded in the hub of the engine, converting raw horsepower into usable speed in ways previously considered impossible. In fighter combat, this translated into life and death. Pilots who had once been matched or beaten by nimble opponents found themselves suddenly having the extra margin. That additional 40 mep in a dive, the extra 1,000 FT per minute in climb. Moments gained that meant they could disengage, reposition, or strike first. The Germans noted it, the Japanese felt it, and soon the Allied air forces understood that the propeller was no longer a passive tool, but an active partner in performance. Behind the scenes, the engineers at Hamilton Standard recalibrated governors, refined blade chords, and tested alloys that could withstand greater centrifugal forces and heat. Thousands of hours were logged in wind tunnels and test beds. Aerodynamic engineers explaining in forums that more blades are more efficient for a faster spinning prop. Meanwhile, in the field, the results were tangible. The 1944 P-47D, equipped with a paddle-bladed, four-blade propeller driven by the 2800 HP Pratt & Whitney R2800, could dive at over 550 pitches and zoom back to altitude when its smaller-bladed opponents gasped for oxygen. The secret blade was working. As production ramped up, airfield mechanics noted fewer prop strikes, fewer stalls in high G dives, and pilots reported wider performance envelopes. What had begun as a small experiment in a factory hangar had rippled through the skies of Europe and beyond, quietly rewriting the margins of air combat. In the months that followed, as the Luftwaffe scrambled to keep up, and as Japanese Zeros found themselves outrun by the new generation of Allied fighters, it became clear the blade, once a simple spinning disc, had become a weapon, and the secret lay in its adaptive design, its ability to extract horsepower where before it wasted it. And in 1945, the true scope of the change became visible. Planes that once engaged in turning fights now climbed and struck from altitude. Formations that once held steady now dove with impunity. The secret blade had shifted the game. By mid-1943, what had begun as an obscure engineering experiment was reshaping the entire doctrine of air combat. The constant speed propeller, the secret blade, as pilots informally called it, was no longer a niche upgrade. It had become the beating heart of a new generation of warplanes. Factories from Connecticut to California were humming with the production of variable pitch hubs, and every crate stamped Hamilton Standard or de Havilland Propeller Co. carried the quiet promise of faster climbs and safer landings. To most outside the hangars, it looked like simple metalwork. But for the engineers who tuned these blades to perfection, it was an orchestration of mathematics, aerodynamics, and mechanical intuition. Each blade was designed like a living organism. The angle near the root differed from the tip, sculpted so air flowed evenly along its length. When the engine roared to life, centrifugal forces tried to flatten it, but inside the hub, hydraulic pressure and mechanical governors fought back, twisting the blade to the precise pitch needed for maximum thrust. What that meant in practice was revolutionary. A fighter pilot could now push his throttle forward during takeoff and get instant acceleration without over-revving the engine. As the plane climbed and air density dropped, the propeller automatically fine-tuned its bite on the air, holding the RPM steady and converting power into continuous thrust. No more wasted energy, no more moments of hesitation. The first time this system went into combat over Europe, Luftwaffe pilots were stunned. Reports from the front described American Thunderbolts that climbed like rockets, and British Spitfires that could dive and recover from terminal speeds that should have shattered their airframes. The secret wasn't more horsepower, it was efficiency. Every drop of fuel, every revolution of the crankshaft was being converted into forward motion with mathematical precision. For a pilot under fire, that margin of efficiency could mean the difference between escape and a flaming descent. In factories and airfields alike, the men who built and maintained these blades took immense pride in their craft. They called it tuning the song. If a blade's pitch control lagged even by a second, it could cause engine overspeed and mechanical failure. So they calibrated governors, checked oil-filled hubs for leaks, and balanced each unit with the care of watchmakers. Engineers like Caldwell worked tirelessly to solve one persistent problem: vibration. As propellers spun faster, harmonic vibrations could tear apart the very engines that powered them. To counter that, new alloys were introduced. Aluminum-magnesium blends, strong enough to resist bending, yet light enough to prevent drag. Every curve, every rivet on the blade's surface was shaped by both science and instinct, honed through test flights that often risked the lives of daring pilots. Among those test pilots was a man named Andrew "Tex" Johnston, later famous for his barrel roll of the Boeing 707, who spent countless hours flying experimental propeller systems. He would later recall that moment when the governor first locked in. You could feel it bite the air. It wasn't just thrust, it was power you could ride, like catching a wave. That sensation became the hallmark of advanced propeller-driven aircraft in the latter years of World War II. By 1944, the innovation had spread beyond fighters. Bombers like the B-17 Flying Fortress and the B-24 Liberator began receiving upgraded propellers, enabling them to climb faster with heavy payloads and maintain tighter formations at high altitude. Transport aircraft, such as the C-47 Skytrain, carried supplies over the Himalayas. The Hump, with variable pitch propellers that automatically compensated for the thinning air. Without these systems, many of those missions would have ended in disaster. Meanwhile, across the Atlantic, German and Japanese engineers scrambled to replicate the technology. The Germans developed their own constant speed systems under the VDM, Vereinigte Deutsche Metallwerke brand, installing them on the formidable FW-190 Dora and Me 109 Gustav fighters. But the Allies had already perfected the balance between blade design, governor response, and material resilience. The Japanese, limited by shortages of aluminum and machining precision, often reverted to fixed-pitch designs that lagged behind in performance. In air duels over the Pacific, this technological gap was devastating. American pilots could dive, pull up, and regain speed instantly, while Zeros struggled to maintain efficiency once the propeller reached its aerodynamic limits. The secret blade didn't just change machines, it changed strategy. Commanders began to plan missions around the newfound capabilities of their aircraft. Fighters could now escort bombers deeper into enemy territory, climb faster to intercept intruders, and conserve fuel on long patrols. Every squadron that received the new propellers recorded measurable performance gains, shorter takeoffs, better climb rates, faster cruise speeds. The innovation was so impactful that Allied intelligence deliberately avoided publicizing its details, classifying the full schematics until after the war. Yet the beauty of the design lay in its simplicity. A small mechanical governor, using nothing more than centrifugal force and hydraulic oil, automatically adjusted the blade's angle to maintain constant engine speed. It was pure physics, harnessed by elegant mechanics. No electronics, no computers, just a deep understanding of airflow and momentum. The more the engine tried to race, the more the governor twisted the blades to ease the load. The more the plane slowed, the finer the pitch became, allowing it to grab more air and accelerate. The result was a seamless, self-regulating system decades ahead of its time. By the closing months of World War II, the constant speed propeller had become a symbol of American and British engineering mastery. It allowed aircraft like the P-51 Mustang to escort bombers all the way to Berlin and back, something thought impossible only a few years earlier. The Mustang's speed, over 440 mph in level flight, was not just the result of its Rolls-Royce Merlin engine, but the harmony between engine and propeller. A duet so perfectly synchronized that it turned air into velocity with almost magical efficiency. What most historians overlook is how close this innovation came to being ignored. In the early 1930s, both the U.S. Army Air Corps and the Royal Air Force dismissed variable pitch propellers as mechanically excessive, too complex for wartime reliability. It took persistent advocacy from a handful of engineers and pilots to prove them wrong. By the time the war demanded every ounce of performance, that persistence had paid off, and the secret blade was ready. From the deserts of North Africa to the stormy skies of the Pacific, its hum became the soundtrack of Allied air power. Pilots described how the pitch system thought for them, adjusting faster than human reflexes could manage. In combat, this mechanical intuition meant survival. In dogfights, in evasive dives, in desperate takeoffs from bombed-out runways. The blade had become a thinking machine, the first whisper of automation in aviation. By early 1945, Allied engineers were already thinking beyond victory. The constant speed propeller had proven its worth, but what it truly unlocked was a new way of thinking about thrust management, the idea that efficiency could be controlled dynamically instead of fixed by design. At Wright Field in Ohio and Farnborough in England, teams began analyzing the flow data collected from combat aircraft, comparing pitch settings, altitude changes, and air density readings from returning squadrons. The results astonished them. Airplanes using constant speed propellers consistently recorded fuel consumption reductions of 12 to 18% and climb rate improvements of more than 25% over identical airframes with fixed pitch props. In aviation terms, those were gigantic margins. The Royal Aircraft Establishment published a confidential memorandum titled Variable Pitch Mechanisms in Relation to Power Plant Efficiency. It concluded that a constant speed propeller effectively acted as a mechanical analog computer, regulating the engine's workload in real time. That insight seeded the first post-war research into automatic engine controls, the direct ancestor of today's FADEC systems. Meanwhile, Hamilton's standard engineers turned their wartime success into peacetime refinement. Their new hydromatic 23E50 propeller introduced a sealed oil pressure circuit that allowed precise feathering, the ability to rotate the blades edge-on to the airflow in case of engine failure. Feathering saved countless lives in twin-engine transports and bombers. A dead propeller could otherwise act like a massive air brake. Pilots flying C-47s and B-25s learned that the moment they hit the feathering switch, vibration vanished and drag dropped away. That single innovation kept the constant speed system relevant long after jets appeared. Across the Atlantic, British manufacturers such as Untold and de Havilland Propellers Limited continued to perfect composite and laminated wood designs for late-war aircraft like the Spitfire Mk14 and Tempest 5. The subtle differences between metal and wood mattered. Metal blades could be forged to finer aerodynamic tolerances, but wooden blades offered built-in damping against resonance. To reconcile both advantages, post-1946 propellers began using metal leading edges bonded to wooden cores, an early example of hybrid material engineering. As the Cold War began, the lessons of the secret blade migrated into jet turbines. The axial flow compressor of a jet engine is, in essence, a series of rotating blades whose pitch angle determines how air accelerates through the core. Engineers who had once calculated propeller pitch now use the same equations to design compressor stages. Sir Frank Whittle, the British jet pioneer, openly acknowledged that his turbine efficiency calculations borrowed from propeller thrust theory. In the United States, General Electric's Dr. Sanford Moss, a veteran of turbo supercharger development, recruited propeller specialists to model blade aerodynamics for the J-33 and J-47 engines. Ironically, just as propeller design reached its mechanical peak, it began to vanish from frontline fighters. Jets like the Me-262 and P-80 Shooting Star signaled the new age. Yet transport and maritime patrol aircraft clung to the propeller precisely because of what that wartime blade had achieved: unmatched efficiency at medium speeds and altitudes. When the Lockheed Constellation and Douglas DC-6 entered commercial service, passengers enjoyed smoother, faster, quieter flights, all courtesy of constant-speed propellers fine-tuned from war experience. In 1950, Hamilton Standard introduced the Hydromatic 54H6, a fully reversible, constant-speed propeller later fitted to the C-130 Hercules and P-3 Orion. Reversible pitch allowed aircraft to back up under their own power or shorten landing runs dramatically. That system remains in use today. 3/4 of a century later, every time a C-130 lands on a short dirt strip and stops within a few dozen meters, it is the descendant of that original wartime idea, blades changing angle faster than a pilot can react. Historians often debate which single invention gave the Allies aerial supremacy: radar, the supercharger, the Merlin engine. But aviation archivists at the Smithsonian's Udvar Hazy Center argue that the constant-speed propeller quietly underpinned them all. In their archives sits a restored Hamilton Standard 23E50, its polished blades mounted beside a cutaway governor assembly. Visitors are surprised to learn that the small, gear-driven flyweights inside that governor are what allowed Spitfires and Mustangs to chase down enemy aircraft thousands of feet above the clouds. During restoration, technicians discovered evidence of wartime field repairs, faint punch marks, and hand-stamped numbers on the hub collar. Notes from mechanics who once calibrated pitch settings with nothing but feeler gauges and courage. Those marks are a physical record of a moment when mechanical mastery met necessity. The influence spread far beyond military use. Agricultural aircraft, bush planes, and early turboprops all inherited the same principle. Even modern constant-speed units on general aviation aircraft, the Hartzell Trailblazer or MT propeller series, rely on a governor concept that would be instantly familiar to a 1940s engineer. The only difference is the medium: synthetic oil, electronic sensors, and carbon fiber blades instead of aluminum. Aerodynamicists later realized that the secret blade's legacy was conceptual rather than purely mechanical. It taught engineers to think of the propeller not as a fixed object, but as a dynamic airfoil system. That mindset directly shaped the design of helicopter rotors and, later, drone propellers, optimized for variable load. When NASA's Ingenuity helicopter flew on Mars in 2021, its counter-rotating blades were adjusted by a computerized governor, an idea whose lineage runs straight back to the 1930s constant-speed mechanism. Yet the human stories remain the most compelling. Many of the men who developed these systems never received public recognition. Frank W. Caldwell, often called the father of the controllable pitch propeller, worked quietly at Hamilton Standard until his retirement in 1956. He was awarded the Collier Trophy in 1933, but his real triumph came a decade later when his invention helped end a world war. Declassified letters show that General Hap Arnold personally credited Caldwell's team for giving American fighters the edge that carried us home. Across the ocean, British engineer W.A. Wimperis, who had championed the Air Ministry's early variable pitch research, lived long enough to see the Spitfire's propeller preserved at the Imperial War Museum. In his notes he wrote, "We sought a better screw and built a new kind of wing." That poetic phrase captures the essence of the secret blade, a wing that spins. By the 1960s, jet propulsion dominated headlines, but whenever an airline pilot pushed a turboprop throttle forward and felt the automatic pitch engage, they were feeling the same invisible hand that once guided a Mustang through the thin air over Berlin. Each whirring blade carried a story of invention born from necessity, polished by mathematics, and proven in combat. By the end of the 20th century, the constant-speed propeller had faded from the front lines. Yet its logic lived on inside every turbine engine and wind tunnel on Earth. The concept that first gave WW-2's aircraft their decisive advantage, balancing airflow and resistance automatically, became a cornerstone of every modern propulsion system. Engineers no longer thought of power as a raw force to be unleashed, but as a harmonized relationship between machine and air. That shift began with a single spinning blade, once dismissed as an unnecessary complexity. In quiet corners of aviation museums, visitors walk past engines gleaming under glass. Few stop long enough to notice the small brass placard that reads "Constant Speed Propeller Governor." It looks unremarkable, a palm-sized cylinder with a few gears inside. Yet those tiny components once determined whether a pilot would climb safely above the flak or stall under its weight. In Alabama and Michigan, restorers still bring old Hamilton Standard units back to life, polishing each part until it mirrors the faces of men who might have flown them 80 years ago. At air shows, when a restored P-51 Mustang or Spitfire Mach 9 taxis out, the crowd feels a rumble that no jet can match. The blades begin to turn slowly, then blur into a transparent disc, shimmering like glass. That blur is the visible ghost of the secret blade. Each flicker of light is a memory of thousands of hands that machined, balanced, and calibrated those edges with wartime precision. As the propeller cuts the air, the sound that follows is more than an engine note. It's a mechanical heartbeat that once defined survival. The pilots who flew these machines spoke of the constant speed system with quiet reverence. It wasn't just a convenience. It was the difference between fighting the controls and flying with the airplane. Veteran pilot Bud Anderson, who flew P-51s in the 357th Fighter Group, once said in an interview, "It felt like the plane knew what I wanted before I did." That intuition came from the propeller governor automatically flattening the pitch as he dove and steepening it again as he climbed, a partnership between man and machine written in oil, pressure and steel. Modern engineers continue to rediscover this relationship. The same feedback logic now controls wind turbines that power cities, drone rotors that stabilize in gusts, and even the fans cooling modern data centers. What began as a wartime emergency solution evolved into a universal law of design: efficiency through adaptability. The secret blade became a teacher. In recent years, historians and restorers have unearthed forgotten documents from storage depots in Connecticut and Bristol, original test logs, showing that engineers experimented with automatic governors long before they were approved for combat. Some of the earliest blueprints, water-stained and brittle, still bear handwritten notes. Try lighter oil, vibration reduced at 2500 RPM. These details tell a human story. Every calculation was born from trial and error, each adjustment from sleepless nights in hangars, echoing with hammer blows and radio static. One surviving engineer, interviewed in 1982, recalled standing on a runway as a new variable pitch unit roared to life. "We didn't know if it would explode," he laughed. "But when it held steady, you could feel it, like the airplane was breathing differently. That moment, the hum between danger and discovery, was what defined the era. The constant speed propeller changed the rhythm of the war, not through destruction, but through control. It allowed more range, more precision, fewer wasted engines. It gave pilots the chance to focus on mission rather than machinery. And in doing so, it quietly turned the tide of the air war, saving countless lives on both sides. Today, when aerospace students study thrust vectors or blade efficiency ratios, they are unknowingly tracing the legacy of the same wartime experiment. The software that governs a Boeing 787's composite fan blades runs on the same mathematical principle used in 1940 to adjust propeller pitch, maintain constant RPM, vary load. Even the Mars helicopter Ingenuity, spinning its blades in the thin Martian atmosphere, uses algorithms derived from that same foundation. Humanity carried the idea of the secret blade not just across continents, but across worlds. In a sense, the invention was more than a mechanical triumph. It was a philosophical one. It proved that progress comes not only from raw power, but from harmony, from understanding how to move with resistance rather than against it. That realization shaped the post-war world. It turned machines of war into tools of science, commerce, and exploration. When the sun sets over an airfield and a vintage Mustang takes off for a demonstration flight, the low golden light catches the spinning blades just right. For a brief moment, they appear almost motionless, the paradox of motion frozen in time. The crowd sees beauty. The engineers would see perfect efficiency. But those who know the story see something deeper, a tribute to forgotten hands, to minds that never gave up searching for a smoother way through the sky. And so, the legacy of that secret blade continues. Not in museums alone, but in every engine that adapts, in every machine that learns to breathe with the wind instead of fighting it. It is the unseen ancestor of all modern innovation, the whispering voice in the metal that says, "Find balance. Let the air work for you." As the war deepened through 1942, every nation in the skies fought a parallel battle, not only for dominance, but for efficiency. The Allies and Axis both realized that victory in the air depended less on the sheer number of aircraft and more on how far and how long those aircraft could fly. Fuel shortages were becoming as dangerous as enemy fighters. The constant speed propeller, once an engineering novelty, was fast becoming the hidden weapon that would decide who stayed aloft. In Britain, the Royal Air Force worked with de Havilland and Rotol to adapt the new propeller system for their Spitfires and Hurricanes. Early versions used wooden blades, carefully laminated by hand, and fitted with a hub that could twist the pitch automatically. Before this, RAF pilots had to adjust the propeller manually using a lever in the cockpit, a tricky, sometimes fatal task during combat. A single second of wrong pitch could cause an engine to stall or overspeed. But with the constant speed unit installed, the aircraft suddenly felt alive, as if it anticipated every command. Pilots could focus on fighting, not mechanics. Across the Atlantic, American engineers at Hamilton Standard were running tests day and night inside massive steel hangars in Connecticut. Each engine was bolted to a concrete floor, while engineers watched the propeller tips blur into invisible arcs. They measured vibration, heat, and thrust with chalk marks and stopwatches, primitive tools, yet precise enough to revolutionize air power. The results were astonishing. Planes that once struggled to climb could now reach combat altitude in half the time. Cruising speed increased, range stretched by hundreds of miles, and fuel efficiency soared. Meanwhile, on the other side of the front, German and Italian engineers were making their own advances. The Luftwaffe's Messerschmitt Bf-109 and Focke-Wulf FW-190 were fitted with VDM variable pitch propellers, which worked on similar principles. Axis designers understood the value of keeping RPM constant. It reduced engine strain and improved climb rate. The difference lay in materials and production. While the Germans had brilliant designs, shortages of lightweight alloys and lubricants meant their systems often froze or jammed in extreme cold. In contrast, Allied planes using Hamilton or Rotoll propellers operated smoothly across Europe, Africa, and the Pacific. One of the most dramatic demonstrations of the technology came during Operation Torch, the Allied invasion of North Africa in November 1942. American P-38 Lightnings and British Spitfires faced sweltering desert heat, unpredictable winds and clouds of sand that could choke any engine. Yet the constant speed propellers adapted perfectly. As aircraft dived, the blades flattened to reduce drag. As they climbed, the pitch increased automatically, keeping the engine's roar steady like a metronome. Pilots described it as riding a tide of power. Colonel James W. Hazlip, a former test pilot turned commander, later recalled in an after-action report, "We were no longer fighting the airplane. We were flying with it." His words captured the quiet revolution that had taken place. For decades, engineers had seen aircraft engines as beasts to be tamed. The constant speed propeller turned them into partners. Factories across the US, from Massachusetts to California, began producing thousands of these units each month. Women working in wartime production, known collectively as Rosie the Riveters, assembled governors, gears, and hydraulic pistons with remarkable precision. Every finished unit was stamped, tested, and shipped to airfields around the world. In black and white photographs from the era, you can see rows of women in bandanas tightening bolts on propeller hubs, unaware that their work would soon define air superiority. For the Allies, this meant something far greater than performance. It meant reliability. Fighters could escort bombers longer. Pilots could push their engines harder without fear of mechanical failure. The system's self-adjusting mechanism kept temperatures steady, oil pressure balanced, and revolutions within safe limits. It was like giving every aircraft its own silent engineer in the nose. Even in the Pacific, where the environment punished machines mercilessly, the constant speed propeller held up. American F-4U Corsairs and P-47 Thunderbolts roared over island jungles, with engines tuned perfectly to altitude and humidity. Reports from the field often mentioned that while the terrain destroyed tires and fuel lines, the propellers rarely failed. Ground crews grew to trust them as the most dependable part of the aircraft. In secret Allied briefings, the innovation was classified as a force multiplier. It didn't fire bullets or drop bombs, but it made every bullet and bomb reach its target more efficiently. Commanders in Washington and London quietly noted how missions completed with constant speed aircraft had higher return rates and lower maintenance costs. In essence, the war effort was learning that victory wasn't just about firepower, it was about endurance. As the months passed, the world of aviation began to shift permanently. What started as an emergency invention had turned into a new philosophy of flight. The skies were no longer conquered by brute force, but by precision, adaptability, and a sense of partnership between human skill and mechanical intelligence. By late 1943, constant-speed propellers were standard on nearly every frontline aircraft. The pilots who once viewed them as complex luxuries now refused to fly without them. And for engineers, the design became a living symbol of wartime ingenuity, a reminder that progress often hides in the smallest details, in the turning of a blade or the hum of a perfect revolution. By 1944, the Allied air forces had gained an undeniable advantage in the sky. Bombing runs over Germany grew more frequent. Escort missions stretched deeper into Axis territory, and pilots trusted their aircraft in ways unthinkable just 2 years earlier. Hidden beneath the roar of every takeoff was the same quiet secret, the constant speed propeller, or as some engineers called it, the self-thinking blade. It was more than a mechanical upgrade. It was a mindset, a symbol of precision that contrasted sharply with the chaos of war. At the Lockheed factory in Burbank, California, mechanics lined up dozens of P-38 Lightnings under the hot sun. Each one gleamed with twin engines and mirrored silver propeller discs, polished until they reflected the clouds. Workers moved between them with grease-stained manuals and checklists, ensuring that every hydraulic governor was perfectly tuned. This careful calibration wasn't just routine, it was what separated life and death. Pilots flying across enemy territory knew that even a small propeller malfunction could drag an aircraft into a fatal spin. But with the constant speed mechanism, that fear began to fade. In field reports, U.S. Army Air Force engineers started recording data that seemed impossible. Climb rates improved by over 20%. Fuel efficiency increased by nearly a third. Aircraft that once lost speed at high altitude could now maintain thrust against the thin air. Every technical gain translated directly into tactical advantage. Bombers reached targets faster and returned home safer. Fighters like the P-51 Mustang, soon to become the most celebrated aircraft of the war, relied heavily on this propeller system to balance its raw engine power with elegant control. One pilot, Lieutenant Charles "Red" Morgan, described his first mission over France with the new setup. It felt like the aircraft wasn't flying through the air. It was part of it. You could sense the pitch shifting under your hand, almost like a heartbeat matching your own. Back in Britain, the Ministry of Aircraft Production commissioned studies on how this innovation was changing the psychology of flying. Their conclusion was fascinating. The constant speed propeller not only improved performance, but also reduced pilot fatigue. Before, airmen spent precious seconds adjusting throttle and pitch, juggling both during the chaos of dogfights. Now they could focus entirely on maneuvering and survival. This mental clarity, though invisible on paper, saved countless lives. Meanwhile, deep inside Germany, Luftwaffe engineers continued their desperate race to match Allied technology. VDM engineers refined their automatic propeller governor, experimenting with new lubricants and faster response valves. They even tested electromechanical pitch controls, decades ahead of their time. But fuel shortages, bombing raids, and resource constraints crippled production. Factories in Hamburg and Stuttgart were hit repeatedly by Allied raids, ironically, by aircraft, whose propellers embodied the very innovation the Germans were striving to perfect. In one remarkable intelligence report from late 1944, British analysts recovered documents showing that German engineers had nicknamed their prototype Der Denkende Propeller, the thinking propeller. It was a recognition that the era of brute force flight was over. From now on, mastery of the skies belonged to machines that could think with precision. At the same time, far from the European theater, American engineers were pushing the boundaries of the concept. On test airfields in Ohio and Kansas, researchers began experimenting with thin-bladed, high-torque propellers, precursors to the variable geometry fans later used in early jet engines. These blades, forged from new aluminum alloys and coated with heat-resistant enamel, were the descendants of that secret blade which had first changed the course of air combat. The connection between propeller science and jet propulsion may seem distant, but it wasn't. Engineers like Frank Whittle in Britain and Hans von Ohain in Germany both studied the aerodynamics of rotating blades before transitioning to turbine design. The principles of maintaining constant rotational speed under changing air pressure, first mastered in propellers, directly influenced the early jet compressor stages. In a sense, the propeller's evolution laid the blueprint for the jet age. As the Allied advance pressed into 1945, constant speed propellers became a mark of engineering prestige. Even Soviet Yak fighters, built under immense wartime pressure, incorporated similar systems based on Western designs. The skies over Berlin, Okinawa and Manila hummed with the synchronized rhythm of aircraft, whose blades automatically adjusted to the invisible tides of air. The world's deadliest conflict was also its greatest laboratory for motion. One of the most poetic testaments came not from a general or scientist, but from a mechanic named Albert Green, who had spent 3 years servicing B-17 bombers. In a letter to his wife, he wrote, "Every plane that comes home feels like a miracle of balance, not brute power, not luck, but perfect timing in every turn of the blade." That sense of balance between technology and humanity defined the closing chapter of the war. When peace finally came, the constant speed propeller was no longer secret. It was a standard, and yet its legacy ran deeper than performance metrics or fuel charts. It symbolized how engineering could evolve under pressure, how invention could emerge from necessity, and how even in destruction there could be creation after the war. Surplus aircraft filled hangars across America and Europe. Many were decommissioned, stripped for parts, or turned into civilian transports. Yet the propeller hubs were often salvaged intact, studied by post-war engineers. These units inspired generations of designers who would later craft commercial airliners, private planes, and eventually hybrid aircraft that blurred the line between propeller and jet propulsion. By the dawn of the 1950s, aviation journals were calling the constant speed propeller the bridge between piston and turbine. Engineers who once built them now led teams at Pratt & Whitney, Rolls-Royce, and Boeing. The self-adjusting systems developed for war found peace in civil aviation, powering crop dusters, mail planes, and passenger aircraft alike. The secret blade had not only made warplanes faster, it had quietly defined the DNA of modern flight. As the Second World War raged across Europe and the Pacific, engineers were in a race against time, not just to build stronger engines or sturdier airframes, but to solve one of aviation's strangest and deadliest problems, compressibility. Pilots flying high-speed dives in the early 1940s suddenly found their control surfaces locked, their planes shaking violently, and their fates sealed by an invisible wall of air. It wasn't bullets ending their missions. It was physics. In this world of desperate innovation came the secret blade, a design so simple yet revolutionary that it redefined aerial combat speed forever. This blade wasn't a weapon in the usual sense. It was a thin, swept shape, carved and tested in secret labs, inspired by nature and refined by mathematics. German and Allied engineers were both working on similar concepts, but the first to understand its power would dominate the skies. At the heart of the discovery was the understanding that air itself behaves differently near the speed of sound. Traditional, straight wings created shockwaves that caused drag and instability. As airspeed neared Mach 1, planes would tremble uncontrollably, the dreaded Mach tuck. Many early test pilots never returned from these dives. They were fighting a new kind of enemy, invisible and merciless air pressure. The breakthrough came when German scientists, particularly at Messerschmitt and Junkers, began experimenting with swept-back wings. Engineers like Adolf Bussmann had already theorized before the war that angling a wing backward could delay the formation of shockwaves. But wartime secrecy meant these ideas were hidden in classified blueprints, long before the Allies understood their value. When Allied intelligence later uncovered these designs, they were stunned. The swept blade wasn't just a theory, it had been built. German prototypes, like the Messerschmitt Me-101 and Me-262 HG series, used this aerodynamic innovation to reach unheard-of speeds. These were not conventional planes. They were the first whispers of the jet age. Meanwhile, across the ocean, in secret U.S. facilities like NACA's Langley Research Center, engineers were conducting their own experiments. They used captured German research and combined it with American test flights. It was there that the North American F-86 Sabre took shape, a plane with wings swept at 35 degrees, mimicking the secret blade geometry. When it finally flew, the results were astonishing. The Sabre could dive faster, turn smoother, and recover where earlier aircraft would have disintegrated. This design would later give the Sabre the edge in the Korean War, where it went head-to-head with the Soviet MiG-15, itself also based on swept-wing research. The dogfights between these two planes were not just battles of skill, but of design philosophy, both sides harnessing the same secret born from wartime experiments. But behind this transformation was a hidden network of scientists who rarely got public recognition. Many were German engineers brought to America under Operation Paperclip, working quietly in US labs. Others were British aerodynamicists who had theorized similar designs but lacked wartime funding to realize them. Together, they built the foundation of modern jet flight. By 1947, the blade concept had evolved beyond wings. Engineers realized that even jet air intakes, fuselage edges, and tail surfaces needed to follow these same aerodynamic rules. The design language of the modern fighter jet, from the F-86 to the F-15, all traces its lineage back to that swept shape born in secrecy. In truth, this was not just a story of invention. It was a story of understanding nature's limits and bending them. The secret blade was more than metal. It was the first time humans truly learned to slice through air itself. Next time you see a jet streaking across the sky, cutting through clouds effortlessly, remember, its power lies in that hidden angle, the invisible blade that turned chaos into control. As the Second World War raged across Europe and the Pacific, engineers were in a race against time, not just to build stronger engines or sturdier airframes, but to solve one of aviation's strangest and deadliest problems, compressibility. Pilots flying high-speed dives in the early 1940s suddenly found their control surfaces locked, their planes shaking violently, and their fates sealed by an invisible wall of air. It wasn't bullets ending their missions, it was physics. In this world of desperate innovation came the secret blade, a design so simple yet revolutionary that it redefined aerial combat speed forever. This blade wasn't a weapon in the usual sense. It was a thin, swept shape, carved and tested in secret labs, inspired by nature and refined by mathematics. German and Allied engineers were both working on similar concepts, but the first to understand its power would dominate the skies. The heart of the discovery was the realization that air itself behaves differently near the speed of sound. Traditional straight wings created shock waves that caused drag and instability. As airspeed neared Mach 1, planes would tremble uncontrollably, the dreaded Mach tuck. Many early test pilots never returned from these dives. They were fighting a new kind of enemy, invisible and merciless air pressure. The breakthrough came when German scientists, particularly at Messerschmitt and Junkers, began experimenting with swept-back wings. Engineers like Adolf Busemann had already theorized before the war that angling a wing backward could delay the formation of shock waves. But wartime secrecy meant these ideas were hidden in classified blueprints, long before the Allies understood their value. When Allied intelligence later uncovered these designs, they were stunned. The swept blade wasn't just a theory, it had been built. German prototypes like the Messerschmitt P1101 and Me 262 HG series used this aerodynamic innovation to reach unheard-of speeds. These were not conventional planes. They were the first whispers of the jet age. Meanwhile, across the ocean, in secret US facilities like Nakie's Langley Research Center, engineers were conducting their own experiments. They used captured German research and combined it with American test flights. It was there that the North American F-86 Sabre took shape, a plane with wings swept at 35 degrees, mimicking the secret blade geometry. When it finally flew, the results were astonishing. The Sabre could dive faster, turn smoother, and recover where earlier aircraft would have disintegrated. This design would later give the Sabre the edge in the Korean War, where it went head-to-head with the Soviet MiG-15, itself also based on swept-wing research. The dogfights between these two planes were not just battles of skill, but of design philosophy. Both sides harnessing the same secret born from wartime experiments. Behind this transformation was a hidden network of scientists who rarely got public recognition. Many were German engineers brought to America under Operation Paperclip, working quietly in US labs. Others were British aerodynamicists who had theorized similar designs but lacked wartime funding to realize them. Together they built the foundation of modern jet flight. By 1947, the blade concept had evolved beyond wings. Engineers realized that even jet air intakes, fuselage edges, and tail surfaces needed to follow these same aerodynamic rules. The design language of the modern fighter jet, from the F-86 to the F-15, all traces its lineage back to that swept shape born in secrecy. In truth, this was not just a story of invention. It was a story of understanding nature's limits and bending them. The secret blade was more than metal. It was the first time humans truly learned to slice through air itself. Every jet streaking through the modern sky, whether in military service or civilian flight, carries a hidden piece of that wartime secret. The next time you hear the roar of a jet above, remember, inside that noise is history itself. A whisper of the invisible blade that changed the world. And that's the story of the secret blade that made warplanes faster than ever before. A hidden innovation that shaped the entire future of flight. If you found this story fascinating, make sure to like, subscribe, and hit the bell icon for more real, untold histories of aviation and wartime science. Until next time, keep exploring the skies where history still flies.